Hello everyone, welcome to Mindspan Education. In this video we are going to look at the covariance of two random variable. Covariance gives you the information about the dependencies of two random variable. This is how we define the covariance of this random variable x and y. This is the notation for the covariance of this random variable x and y, and it is equal to the expected value of the product of deviation of this random variable x and this random variable y from its mean. So it is the product of the deviations of random variables from its mean, expectation of the product of the deviation from its mean. So this is what the covariance is. Let's try to have an insight and let's try to find that what kind of information that we are getting from this covariance. Let's suppose if this covariance is greater than 0, covariance of this random variable x and y is greater than 0. What we can say about this deviation? If this greater than 0, what we can say on average about the product of this deviation? So if this covariance is greater than 0, then on average x takes the value that is greater than its mean and y also tends to take the value that is greater than its mean. Or maybe we could have the case if this covariance is greater than 0, then on average random variable x takes the value that is less than its mean, and at the same time y also tends to take the value that is less than its mean. So this difference would be negative and this deviation would be negative, and overall we will have the positive covariance. So what we can say, if covariance is greater than 0, on average this x and y tends to move together. If x takes on average, if x takes the value that is greater than its mean, then y also tends to take the value that is greater than its mean, right? Or maybe x takes the value that is less than its mean and y also tends to take the value that is lesser and it is less than its mean. So basically what we are trying to say is that if covariance is greater than 0, then on average this x and y tends to move together. And what happens if we can say that this covariance is less than negative? In this case, the x, on average x tends to take the value that is greater than its mean, and at the same time y tends to take the value that is smaller than its mean. So in this case x and y are not moving together, they are opposite to each other, right? So this deviation would be positive and this deviation would be negative. So overall we will have a covariance that would be less than 0, right? So what kind of information that you are getting from this covariance? The covariance gives you that how these two random variable tends to move, right? If they move in the same direction or if they are moving in the opposite direction. Alright, let me take a very simple example so that you have a good picture there. Let's suppose if we have this random variable x and y, and we have the PMF of this joint random variable x and y that is distributed over this region. Right, so we have the probability is distributed over this region and all these have the equal probability, right? So if you look at this plot, the larger values of x tends to take the larger values of y, right? And similarly for the negative side as well, larger values of x tends to take the larger values of y, and similarly smaller values of x tends to take the smaller values of y, and similarly on the negative side. And if you look at this plot, most of the data are in the first quadrant or in the third quadrant, right? And there are very few samples that are in the second quadrant and in the fourth quadrant. And so here the random variable x and y on an average tends to move together. If x is large, then y also takes the large value on an average, and if x is taking the large negative value, then y also tends to take the large negative value. So if we try to find the covariance in this case, then we may expect that this covariance would be greater than 0. So let's also assume that the expectation of this individual expectation or the mean of this random variable is 0, and this y is also 0, right? And now the covariance would be simply the expectation of the product, right? If you put the 0 here, then this covariance would be nothing but the expected value of the product of this x and y. Now let's so what we are here asking, given this PMF, joint PMF, we are asking about the covariance, right? And our intuition says that it would be greater than 0, because here by looking at the plot we can say that the x and y tends to move together on an average. So look at this product, so x times y. For this quadrant where the most of the points are there, most of the samples are there, for this quadrant the product would be greater than 0, and for this second quadrant the product would be less than 0, x times y. And for the third quadrant where most of the points are there, this product would be greater than 0, and for this fourth quadrant where we have few samples, this product would be less than 0. So on an average, if I ask you what will be the expectation or what would be the average value of this product, that is x times y, right? So most of the points that belongs to here in the first quadrant and the third quadrant, and we have seen that product is greater than 0. So on an average, or the expected value of this product that we can say will be greater than 0, right? So if covariance is 0, random variable x and y tends to move together. We could have a example where we could show, let's suppose if we have the distribution of this random variable x and y. So here we can show on the x-axis. Let me first of all rectify this one here, or it is fine, but let's be consistent here, right? Let's suppose we have the samples or the probabilities are distributed like this in two-dimensional space, right? And each one have the equal probabilities, and probabilities are distributed within this region, right? And if you look, sorry, here it will be y, and this is x. This will be y and this is x, right? Now let's look at this plot. So if you look at this plot, now the x and y are moving in opposite direction. How? Look at these values of x. So x is taking the negative large value and y is taking the positive large value. So if I ask you in this case what will be the on an average value or the expected value of the product of this x and y, right? Because most of the points are falling in this quadrant and most of the points are falling in these two quadrants, and here the product is less than 0, and here also the product is less than 0. And if you look at the total trend of this data, then you can say this, the on an average the expected value of this product, that is x y, would be less than 0, right? So in this case the random variable on average tends to move opposite to each other. If x takes a larger positive value, y tends to take the larger negative value, right? So in this case the covariance is less than 0, negative, right? So this is the special, so this is also the covariance, right? And this is the special case where we have assumed that the mean of these random variables x and y are 0, then the covariance would be turns out to be expected value of the product of the random variables, right? And in general this is how we have defined the covariance, right? Okay, now let's look at the case when this random variable x and y are independent. So what is the covariance? So if x and y are independent, right, then these can be written as the product of their individual expectation. So expectation of the deviation of this random variable x from its mean times the expectation of the deviation of this random variable y from its expected value or from its mean, right? And this would be the expectation of x minus expectation of this is some constant, that would be the expected value of x, and times expected value of y minus the expected value of y. So that would be 0, right? So if we have the two independent random variable, then covariance would be 0, right? But here the point to note is that independence of this random variable imply the covariance will be 0, but its converse is not true. You cannot say the covariance is 0, then it is guaranteed that the random variable x and y will be independent. So the converse is not true. Let me write down that also. Let me take an example where, so if two random variables are independent, then covariance is 0, that is guaranteed. But you cannot say if you have got the covariance 0 and you do not have any info about this random variable, if you have got the covariance 0, that you cannot comment on that these random variables will be independent or not. Let's take an counter example so that we can see directly from the example that the covariance is 0, but it doesn't mean that it is the random variables are independent. Let's suppose you have this joint distribution of this random variable x and y. So you have the 4 samples, and let's suppose this is 0 1, this is x can take the value that is 1, y will take the value 0, x takes the value 0, y takes the value -1, x takes the value -1, and y takes the value 0, right? Now let's try to find the covariance here. So the covariance is covariance of this random variable x and y is the expected value of the product of the deviations from their mean, so x minus mean of this random variable x times y minus the mean of this random variable y. So what is the mean of this random variable x? So by symmetry you can see, so this is x, right? So these are the two, so by symmetry you can see the mean would be 0 of this random variable x, and what will be the mean of this random variable y? So by symmetry you can directly say the mean would be at 0, right? So the covariance of x and y is equals to expected value of x and y, right? And if you look for any pair x and y, the product will be always 0. So here what we have got is the 0 covariance. Now look at the samples. If I tell you that x takes the value 1, can you say anything about y? Definitely you can say. If I tell you that x takes the value 1, you can easily say that y will be always 0. Y will take the value 0. If I say that x will take the value 0, So this is that just the one. By just saying this, you see, you got the dependence, right? If you know the x, you get to know what will be the y, right? So there is some dependence. So these random variables are dependent. So what we have got is zero covariance, but these random variables are dependent, right? So that is why independence means covariance is 0, but covariance is 0 doesn't mean that the random variables are independent. Let's look at the few of properties of this covariance. Let's look at the very first property. What if I ask you the covariance of this random variable x with itself? So you can easily find that what it will be, right? It will be the expectation of this random variable x from its mean times the another random variable is again x. So the expectation of this random the deviation of this random variable x from its mean, right? So what we have here is the same thing, right? So this time this, that would be the expectation of the deviation of random variable x from its mean ka square, and we can easily recognize that this is nothing but the variance of this random variable x, right? So what's the variance of this random variable x is how we define the variance of random variable x. It is nothing but the expected value of the square distance from its mean, and this is what we have got. So the covariance of this random variable x with itself will give you the variance of this random variable x. We have seen one more alternative formula if of this variance, and that we have used many times while calculation. The alternative formula that we get is by expanding this, right? And let me write down that directly. The variance of this random variable x is nothing but the expected value of this random variable x square minus expectation ka square. We could have similar type of this alternative formula in case of the covariance as well. Let's try to find that one. So we have the covariance. So what we are going to find is the alternative formula that will helpful while doing the calculation of the covariance, while finding the calculation of the covariance. So covariance that we have here is the expected value of the product of deviations of these random variables x and y from their mean, right? And what we can do, we can simply multiply these two, and then we can apply the linearity property of the expectation. So let me first of all multiply and get all the terms. So if you multiply this x times y, you will have xy, and now x times the expected value of y. So x times the expected value of y minus y times the expected value of x times plus the expected value of x times the expected value of y. So these are the four terms that you will get. Now you can apply the linearity property, and this expectation would be equal to the expectation of this random variable x minus the expectation of this random variable x times the expectation of y minus the expectation of y times the expectation of x plus the expectation of the expected x times the expected value of y, right? So this will be the expected value of x times y minus, now this term, that is the expected value of y, will be constant. So we can pull out outside of this expectation. So the expected value of y times the expected value of x minus, again this will be a constant that we can pull out of this expectation. So the expectation value of x times the expected value of y plus these will be the constant. So we will have the expectation of this x times the expectation of this y, right? And these two term will get cancelled because they both are same. So what we have got is the expectation of xy minus the expectation of x times the expectation of y. So this is the alternative formula of the covariance of this random variable x and y, and we can make use of while doing some numerical calculation, right? So we can directly make use of this formula instead of this one. Alright, now let's look one more property. Let's suppose if you have two random variable x and y, and also assume that the mean of each x random variable, that the expectation of this x and the expectation of this y is 0, then what will be the covariance of this? So what we have done here, we have made so here we have a linear function of this random variable x times this random variable y. So we wanted to find the covariance of this. So how we can proceed? It is simple, right? If we have the zero mean, the covariance is nothing but the product, right? Just now we have seen in the very first explanation when we were discussing this, right? If we have the zero mean, then the covariance is nothing but the expectation of the product of these random variable, right? So if the expectation is 0, the covariance is nothing but simply the product, the expectation of the product. So the product of this random variable is ax plus b times y, right? And now further what we can do, we can simply do the algebraic calculation here. So here it will be a times xy plus b times y, and now we can use the linearity. So it will be a times the expected value of xy plus b times the expectation of y. And since the expected value of y is 0, so this will be 0, and overall we will have a times, and if you recognize what is this is nothing but the covariance of random variable x and y, right? So overall point is that if you have two random variable and if their expected value is 0, and if you have some random variable and if you are trying to find the covariance, that is a linear function of this random variable x comma y, so this b will have no effect and the covariance will get scaled by the same quantity, that is a. Let's look one more. Let's suppose we have the random variable x, y and z, and each of have the expected value that is 0. If I ask you that what will be the covariance of the random variable x and the sum of y plus z, so what will be this covariance? Let me know in the comment section. So your answer should be in terms of the covariance of x, y or x, z, whatever. So you can proceed how I have proceed. Expectations are 0, right? So the covariance would be nothing but the product of the expectation of their product, right? And do the algebraic manipulation, you will find something and you will got your answer. So let me know in the comment section what will be the answer to this question, right? Let's try to look at one more thing, and we have already seen if Let's assume we have these two random variables x1 and x2, and these two random variables are independent. What is the variance of the sum of this random variable? We have already seen it is nothing but the sum of the individual variance. What happens to the case if these two random variables are dependent and we are trying to find the variance of the sum of this random variable? Obviously we will have some covariance term as well if these two random variables are dependent. Let's try to expand and let's try to see find the variance of this sum of this random variable. From the definition we know the variance is nothing but the square distance from the expectation of the square distance from the mean. So this is the random variable, and we need to find the distance from its expectation value, that is from its mean, and we need to find the square expectation of the square distance from the mean. So this is the random variable. What we have found is the distance from its mean, and we need to find the expectation of square distance from the mean, right? So we have used the definition of this variance. Now what we can do, we can simply arrange. So first of all, let's use the linearity and let's expand this one. So the expected value of the random variable x1 x2 x1 plus x2 minus, using the linearity we can say that it is the expectation of x1 minus the expectation of x2, right? And this whole square term will be always there. Let's try to rearrange the few terms here. So here we will have x minus expectation of x1. So what we have done, we have combined this, we have written these terms, and now we will have this term, that the x2 minus the expectation of this random variable x2, and do not forget this square term will be there. We have now two terms. This we can consider it as a, and this we can consider it as b, and here we will have a plus b ka whole square, right? So a plus b ka whole square is a square, that means a is this one ka square, plus b square, so b is this one, so this one ka square, plus 2ab, so 2a is this x minus the expectation of x1 times b, so b is x2 minus expectation of x2. Now use the linearity on these, right? So the first term, that would be the expected value of x minus expect ka whole square, and recognize this term. What is this? And the another, I am going to use the linearity, so expectation of x2 minus iska whole square, plus the third term 2 times expectation of x minus expectation of this random variable x1 into x2 minus the expectation of this x2. So you just now need to recognize these terms. What is this? This is the expected value of square distance from the mean of this random variable x1. So this is nothing but the variance of this random variable x1. What is this term? This term is nothing, so it is square distance from the mean. Expectation of the square distance from the mean is nothing but the variance of this random variable x2. And what is this term? This term is nothing. What you are trying to find is this is the deviation of random variable x1 from its mean times the deviation of this random variable x2 from its mean, and you are trying to find the product of these expectation of the product of these deviation. So this is nothing but the covariance of this random variable x and x2. So here we will have 2 times the covariance of this random variable x1 and x2. So we have this relation: if the random variable x1 and x2 are dependent, then the variance of the sum of this random variable x1 and x2 will be the variance of this random variable x1 plus the variance of this random variable x2 plus 2 times the covariance of this random variable x1 and x2.